So this is the paper this week. So it's anyway, have you guys heard of the robotics, like experimental robotics, where you run experiments with robots? That's what this is about, this thing. So then it's usually coupled with artificial intelligence. So you try to get, for artificial intelligence, you need a huge data set. In other words, 10,000 experiments, and feed it in, and then you can sort out like to predict what the result would be, more or less. So I guess I'll talk about AI and this kind of thing when we do simulation stuff, because it's got to do with computers, but not necessarily. So they've got they have a robot. So there's some videos of the robot in here. Let's see. Blah, 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 blah. Source data. This is a supplementary video. So they show the robot running the video. I guess it downloads the video and we run it. So it's trying to run. This thing's blinking. That's the robot. So the robot, it's got a rail, it runs on a rail, and then it can take, so they're using powders, so it's powder ceramics. So they mix together different powders. See, it's kind of annoying. Each one of these is like a separate little 15-second video, but it would be nice if they were just one video, because you probably want to look at all of them if you're looking at one. Let's see, so this guy's mine again. I have to go there. And then they put it into an oven. So they can mill it, has a ball mill in it, that ball mills a sample, then it puts the sample into an oven furnace. So it does the firing of the ceramic, and then whatever reaction happens to make kind of a product. And then it's got a diffraction set up on it. So that's dosing the powders. Anyway, each one of these videos kind of shows another part of it. And then finally they do the diffraction. Let me figure out where it goes. It goes here, and you have to double click there. I think this is a diffraction one. Anyway, it doesn't really. So anyway, I guess that's the automated powder dosing. That's the same thing. That's not the one I want. The diffraction. Anyway, it does a diffraction on it too. It does it by, looks like it's kind of complicated how it does it. Anyway, so it can run, it takes 8 hours per sample to run through the cycle. And then basically they're going to run 224 samples through it. And it can run multiple samples at once. So they kind of, so they've gone to the, they've gone to this lab, and it's a Michigan team, and then they go to a lab in Cambridge, Mass. It's a Samsung lab, I guess. Oops, that's their data set. So anyway, so that's kind of the operation here. You can see they're all at Michigan, and then this Advanced Materials Lab, Samsung Advanced Institute of Technology, America, Samsung Semiconductor. And if you try, so the robot they're using is called this Astral. So it looks like if you got in touch with Samsung Institute of Technology in Cambridge, Mass, you could also go use Astral to mix your own things, like if you're making powder ceramics. I guess anybody can use it, more or less. It seems like. So they're just using this thing. So this is a popular topic, like everyone's doing this kind of automated experiment approach to the government especially is interested in this. So the idea is like you can fire all the lab workers, and you can just set up robots doing all the lab work. And the AKA the robots like the really low cost labor. And then there's some other advantages, like for a company like Samsung, there's an advantage that some small shop operation isn't going to be able to compete. Like if this is the only way you can develop a new cathode for a battery, and so basically if this is really the way to do it, then some small operator is going to be able to afford the Samsung robot. Right, so that cuts out any kind of lower competition, like some kind of small scale enterprise coming in. And then an advantage of this robot thing is like, again, you can make a huge amount of data with it, so it can feed into artificial intelligence. So instead of web searching to get data or running a lot of experiments with people, you can have this robot just generate information. It can be on the fly, so you can do the artificial intelligence analysis of the data at the same time you're taking the data. And then that can guide what data you take for the next thing. So you can kind of do machine learning to get that to work. And then they claim there's a potential to remove errors and get a more reproducible result by this process because there's no human error in it. So that's kind of an interesting thing. If you look at the machine, if you actually look at the videos, which I wasn't able to actually get the ones that are messy, but it doesn't look that, like I think maybe the diffraction one. See if it actually downloaded it. See, it ends up, some of them look kind of like, see the junk that's spilled all over the place. It's like, is that really a clean sample? And is there contamination from the robot arm every time it reaches in? And some pieces fall off when it dumps it in, it doesn't notice. Right. So this idea of like reproducibility, a person would see that the crumbs of the thing fell off, for instance. And so I'm kind of wondering about the reproducibility issue, whether that's true or not. Like I think a lot of this is they already paid the $5 million for the robot and they have to use it for something and kind of making it look good. And then there's a potential to make like unlimited number of tests. Like you don't need to worry about, it's an 8-hour test. If you do them all 250 at once, it takes 8 hours versus 10 years. Right. So the idea is like you can expand the number of experiments you can do. And then the downside to this robotic thing is that there isn't someone that understands what's going on. So it's basically like trained monkeys. Like, do you really want trained monkeys doing your science research for you? Right. So no, you probably wouldn't, because most of the discoveries that people make usually start out on a project with some target goal. Then you're going to be doing your work. And then basically along the way, you discover something. Right. So just because you're in the lab doing things and then you notice something, or it changed to purple, and all of a sudden you realize, oh, instead of making a superconductor, I made like a super purple dot. Like the robot's not going to notice that. So people are better than robots at finding things that you don't expect. Right. So robots might be able to do a lot of work, basically they're not going to discover anything new in that process, and they'll ignore things that happen that could lead to other more important discoveries. So and this thing has no pathway to innovation, really. Right. So those are kind of two of the downsides that I could think of for this. But basically, you might think of some other downsides to this, other than what I'm saying. But anyway, so that's anyway. So this is a pretty common thing because it's like so popular. It's in Nature. It's a Nature paper, even though they don't do much on this. I mean, it isn't normally this would be a paper that wouldn't be in Nature, but because they have a robot doing the work, all of a sudden it's elevated significantly. So the idea is that you're going to make these kind of complex oxides, like mixed oxides, like we saw last week, like trying to make a cathode. I mean, one of the main things is like the cathodes for lithium-ion battery. Then he's saying high temperature superconductors, solid oxide fuel cells. So, and then solid electrolytes. So if you have a battery, then you're going to have this fluorinated lithium solvent in it as the electrolyte. right? And that stuff is the stuff that kind of catches on fire when whatever happens to a lithium-ion battery, if it breaks open. Like if that fluorine touches air, it turns into HF, one drop of which will kill a person. Right? Like one drop of HF will dissolve all the bones in your body if it absorbs, and you can absorb it through your skin or your eyes or whatever. Right. So when you see like a yellow gas coming out of a catalyst type thing, run away. It's the idea. So a lot of the catalysts are fluorinated materials. But anyway, so so solid electrolytes is a big topic because they can get away from that kind of flammable material, and the battery should last longer. So you should be able to have a better battery if it's a solid electrolyte versus liquid. And then making cathodes, and then a lot of like fuel cells are also kind of electrochemical systems. So you're talking about ion conduction through solids, or ion storage in solids, right? So basically all those materials require these kind of complex oxides where you're swapping out like one metal ion for another in the oxide, like lithium for whatever, cobalt, right? In the cathodes. Anyway, so how do you make those things? So in the lab, they make it with, make a solution of a lithium salt, and then you're going to mix the liquids together, right? So you can mix all the liquids together, and then hopefully the compound that you want to make is going to be like the lowest energy compound of the group, right? But the problem is, so with powders, it gets to be more complicated because powders, the kinetics are a lot slower, right? So industrially, when you're making it, it's not going to be from lithium salts in some kind of solution. It's going to be like mixing powders together, ball milling the powders. So it's a dirty process, and it's got a lot of kinetics involved in it. Like in other words, it isn't just a thermodynamic phase diagram that you're looking at. So because of that, and because it's a complicated space, so in this paper, they just talk about ternary mixtures. So they have like 3 oxides that they mix, like this boron oxide, barium oxide, and lithium oxide. So you can buy those powders and then you can mix them together. And they make the claim that when you mix, so these are going to be particles, like crystalline particles of these oxides. And when you mix them together, there's going to be certain reaction pathways that are favored. In other words, and there's going to be a binary reactions. In other words, the green one will react with the red more rapidly than the green with the blue or the red with the blue. Basically, the pathway, if you mix 3 of these together, you're going to get certain pathways that are binary pathways to get to the ternary product that comes out. Right. That's kind of the idea of this. So finding those pathways isn't like trivial, right? So basically, I mean, there's going to be a lot of, so with the 3 things that you combine, there's a lot of different compositions and temperatures that you could use to try to sort through like the kind of the phase space of these things, right? So to try to get some particular product that you're targeting. So the first thing, like they give 2 examples, and then the supplemental gives, I think, 35 total. So there's 33 in the supplemental and 2 in the actual paper to kind of simplify it, I guess. So they're running this robot. So just for one of these, they have 224 reactions that they run through the robot. And they're running 35 of them. So it ends up being thousands of reactions that their robot's doing. And so anyway, so it's a high dimensional space. And it can also, in the normal mixture, it's going to be more than a 3 component to get the product. So it's going to be like, they're using 3 because that's the largest you could get, the smallest you could get and still draw a phase diagram, right? In other words, there aren't coordinary phase diagrams really. So the best you can do is a ternary phase diagram. So they have the three ceramics that they mix together, right? And the composition space is in the middle. And then on the y-axis is this thing called reaction energy. So you want to have a big change in energy from the you want to have a big drop in energy from the reactants to the products. That means you're getting a lot of enthalpy out of the reaction. And to calculate the enthalpy, they can do 2 things. So they can go to this thing called the materials project, which is linked on the web page. You can go to this, and it'll give you the energy. It'll give you all the information about materials, like basically any material that you put in. It's free. So basically, it's kind of like the NIST web book, but it's more for metals and ceramics. NIST web book is a little bit for organic materials. It gives a crystal structure. It gives all the thermodynamic information, electronic structure, the spectra for it, heterostructures. So basically, these are like examples, but you need to register to get it to actually function. There's apps in this thing too. So basically, this is kind of like a place, if you're doing artificial intelligence and need a bunch of data. So they have 154,000 materials cataloged with all the information about it, and some kind of thing that could be accessed by a computer program. So they could just pull out the information it needs. And then you could do artificial intelligence on that to figure out what product you want to make, or what's the, if you put two things together, what's going to form from it. And kind of use this to do that, with including it with some kind of artificial intelligence setup. You can see like they have fluorescence spectroscopy. So this is density functional theory kind of things. So they have simulation results, crystal structures, some diffraction. So everything's kind of here, and every material has different kind of, they all categorized the same way, but they aren't all filled out with the information. This gives the dates for when the information's been added to it. Anyway, so they use that. And then they also use density functional theory, which allows you to, using the waveforms for the electrons and the atoms that are in the crystal, that allows you to calculate the kind of the reaction energy to produce products. So that's like a simulation. It's going to give you some answers about which things are the better things to make. Right. So by combining the DFT, a web search for kind of information about what oxides are used to make certain combined oxides, or things like cathodes for lithium-ion batteries, and using the DFT to get the kind of the energy here, they're able to make these ternary plots. So again, ternary plot, like at the corner, you're at your pure compound, right? And then it's baryocentric, meaning that it's already, in other words, the stoichiometry. Normally in these kind of reactions, you have to worry about the stoichiometry of the reaction. So you have to make sure that the product has Ba 4 or something. Then you have to make sure you have 4 bariums, or Ba5, and make sure you have 5 bariums, and that has to be 5 BaO to get to that point. Right. So then the oxygens have to add up. So, but basically, this is baryocentric, meaning that it's already, those things are already done in this plot. Like you find a point here, it's going to have the right combination of everything to get the mixed oxide that comes out. So you don't have to worry about stoichiometric calculations in it. And then, so anyway, so the corners of this are the pure ingredients that you put into it, the pure oxides. And if you go along a face, like the blue face, and that's a binary combination of barium oxide and lithium oxide, with no boron oxide and lithium oxide with no barium in it. Right, so that fits exactly into this picture, that you put the particles together and then only 2 of them are going to react with each other, because if red and green react, there's no space for blue to fit in there. Right, so these particles can only react in binary sense. And then whichever reaction, red, green, or red, blue, is faster, that's the reaction that's going to lead to the pathway to the product. And so it's kind of kinetically determined. The kinetics is governed by this reaction energy that's a driving force for the kinetics. So all these things are ignoring the entropy. None, like the DFT doesn't give you entropy. In the free energy, which is really governing it, it's going to be the enthalpy minus T delta S. Right. So without the entropy, you're kind of missing something. So all these things will say, like, oh, we can ignore entropy for whatever reason, like just ad hoc. Right. So that's a little bit of a flaw, but they do talk about it in the paper, or they mention it. So anyway, the idea is like there's a possibility to make byproduct phases. Like if you go to the second one, so they're trying to make this phase, this yellow star phase, from lithium oxide and this zinc phosphate, right? So basically, yeah, you could make it from those two, but there's something that has a lower energy, zinc oxide and lithium phosphate, that's got lower energy than the product that you want. So that pathway isn't a good pathway. In other words, this kind of byproduct phase is a common thing. So if you're just randomly mixing things together, you're not necessarily going to get the thing that you want. Or it could be a case where there's not enough driving force, so it's not deep enough in this reaction energy level to drive that reaction. The kinetics make it so slow it would never happen. Right? Where there's other reactions like this, it would happen so fast, so it would just make that. Right? And then this is one where there's a case that's a good thing. Like that's the target material, it's the lowest and highest energy of reaction. So that one would go. So these would be a good pair for the starting oxides to work with. Somehow, if the material you have is lithium oxide, phosphate, and let's see, is it two kinds of phosphates in this one? So it looks like, I don't remember this one exactly, but so anyway, if those are the starting materials that you have, you'd probably want to get this that reaction going first, like somehow make the LiPo3 first, which is a product on one of these curves, right? So on one of the side curves, you can get the product. So basically, if you look here, so what they have a ternary diagram. Pure components are at the corners. And if you go along the side here, there's none of this barium oxide. So it's just boron and lithium, right? So that kind of slice out of this 3D diagram is going to give you, the blue one is going to give you like the barium oxide, lithium oxide. What's the minimum? What's the most likely thing to make? And it's going to be this oxide, mixed oxide. And then along the green one, which is on the back, there's no lithium in it. So basically, you're going to get. So if you plot out the slice on that, right, then you get this green curve, right? And that tells you the minimum there. Then neither of those are going to be the product that you want, which is this lithium, barium, boron oxide, right? So one way to get it would be to go along that and then find a minimum there, like LiP409. And then mix it with that. So do that reaction on the other reaction first and see if those two would give you that. So you could map out on this 3D, like would those two give you a pathway to the lowest energy thing? I mean, it turns out that doesn't work. So anyway, they sort out the best pathway. So all this is done without the robot. Like this is just done with density functional theory. They make these plots. They predict like where the thing's going to go. And then they have a target and they're going to say like, well, because it ignored entropy and it's just a computer simulation, can we believe that that's true or not? So then you have to test it with an experiment. But in order to test that with an experiment, like you have to draw this 3D space, which involves at least 224 separate reactions where you mix the oxides and anneal and calcinate them and then put them in a diffraction to see what product you get out of it. And so they show a little bit of the results. This is the kind of result they get is like, this is their target compound, and there's like none of it in the top one, and this one 900C has some of it. It's like they're kind of using the diffraction patterns to tell them if they've reached the goal that they want. And they're guiding the experiments that they do by the DFT predictions from 3D plots. That's more or less the theme of this thing. But he says it's a mixture of human and robotic chemists. These people are dangerous. Like, like the words they're using are sounding a lot like the robots are taking over the earth. Right? So let's see. So in the end, he's got, so what the robot does is powder preparation, ball milling. It's got 4 steps. Powder preparation, ball milling, oven firing, which would be like 8 hours, then diffraction measurement. So in total of that, it's going to take like 10 hours to do one sample. But it can be doing, in other words, it can be doing ball milling while it's doing oven firing of a different sample. So the robot can kind of amplify a little bit what it can do. Also, like if along the way, I mean, you can use artificial intelligence. They didn't do this, but to look at the results you're getting from each compound that you put in, you might want to modify what you mix for the next compound, right? So it's possible to have a computer tell the robot what to make next to explore this phase diagram. Like if you have 10 samples through here and it's just going through a smooth surface and you don't expect anything strange, then you can skip the rest of to get there and just say, I'm going to measure over here. And then the artificial intelligence, the way it works would be like to say, pick some random places sometimes, but mostly like use kind of logic to figure out where to go in the plot. So there's various algorithms to search out a 2D space like that, to figure out where you'd want to get points to verify what you think the surface is of it. So anyway, it's possible to have AI guide the robot compounding machine. That's the game that people are trying to get into mostly. So his goal is to identify the best precursors to get a target oxide. He's trying to get this lithium barium borate to be for his cathode material. So what's the best starting materials to put into the ball mill, right? And what composition should he start with? Let's see. So that's that business. So then he comes up with these rules. So he has a set of rules here to live by this. And again, this is all before he touches a robot. So he says, so basically he's saying that one of the binary reactions is going to be faster than the others. So you want to start with just mixing 2 together. So you don't get simultaneous pairwise reactions between 3 or more precursors. I guess that simplifies the situation. And that limits what he can make, but basically that's his rule. And then 2, so he's looking for precursors that have a high energy relative to the product. So he wants to get this case where, like this, like he has the precursors way up here and the product way down there, and he's just going to zip along and get to that. And then the intermediate stages of that, he wants to have higher energy. So the first steps, he wants to have a low energy drop or moderate energy drop. So he still has a lot of energy left to give to get to the product. And that's his rule 2 here. Because for relatively high energy, the target material should be the deepest point on the reaction convex hull, such that the thermodynamic driving force and nucleation is greatest over the competing phases. Then the composition slice from between the 2 precursors should intersect 2 other competing phases as possible, minimizing opportunity for undesired reaction products. And then byproducts, if they're unavoidable, the target phase should have a relatively large, like a lower energy or larger energy drop compared to the target phase space. So he kind of shows that in this, I think the first one is more or less, let's see, the first one, let's see. So the total reaction to get to this, the product, this lithium barium borate, it's like 336 milli-electron volts per atom. It's kind of weird units. All right, so because he does that, the units are weird for this, because in order to do this, like you're always dealing with different stoichiometries of different components. So he says like, he's not going to deal with that at all. He's not going to consider the stoichiometry at all. He's just going to consider the product and say for one lithium atom through this process to make that, what's the delta E? What's the reaction energy to get to that product, no matter what I put in at the start. It's kind of a weird idea. Anyway, somehow he calculates that. I don't know exactly how he'd calculate that. Basically, he gets this EV per atom, ends up being milli electron volts. And then 100 would be a large number on that scale. So he's got 200, he got 336 for the reactants. So the product, but to get to that product, there's a lot of divots on it. This looks a lot like the idea of like a free energy diagram for protein folding. It's the same idea. Like he's kind of got a free energy diagram, and it's got many small divots on it where you get trapped. Right. So you can make you can make like things that drugs that don't work by the same kind of process. So you can see the stuff is like kind of becomes universal a little bit, like so the techniques you'd use to mix the things together are different, but the software that you'd use to run the whole thing, like this machine learning and artificial intelligence and the robotic testing, like it doesn't care if it's mixing liquids or if it's mixing solids. It's running a ball mill and an XRD, or it's doing circular dichroism and some other kind of, it could be growing bacteria or something. Like it could be doing anything. So that's why the power of this is kind of like the software package and the kind of approach to it and the math that you use is all going to be identical, like no matter what you do on this. So that's why people are looking at the robotics as taking over everything. So on the other hand, the flaws to it still exist. We're just not gonna, it's gonna walk right over obvious things that would be very useful. Like the Post-it glue, was invented by accident at Dow Chemical. And a secretary said, like, can I use that stuff to glue this paper on the wall? And like the secretary kind of invented Post-it glue. And the chemists that were making it didn't even notice that it would have any use. They found like a glue, they found this, they were trying to make something else and they made this gooey stuff. Or Teflon was invented when they found out that the fluorine tanks were clogging up when they're doing fluorochemical reactions for like coolants, like chlorofluorocarbons, basically. When they said like what's clogging up the tank, and they welded the tank apart and they found out it was coated with Teflon on the inside. So it's like a robot isn't going to discover Teflon. It's not going to discover Post-its. It's just kind of like that's, I think almost like that's almost the normal way things are discovered. It's like we're thinking along one track, we're trying to make a coolant for something, and then you discover Teflon on the road to it. It turns out Teflon's like way more important than any of the other things that you're looking for, right? So the robots are just going to walk right over those things. Right? So anyway, so that's my anti-robot thing. But anyway, so anyway, this for this problem, like framed up the way they framed it up, yeah, it totally makes sense. Right. In general, like you have to wonder, like, is it going to be worth the 10 million bucks for the robot? Like you could have done a lot of experiments with that and maybe done something useful instead of, so it's like, right, put it this way too. There has not been any, so it's been like 10 years, maybe 15 years since this robot and artificial intelligence has been around. There has not been any major discovery by this route. So you'd think like, and the amount of money put into it is probably, maybe hundreds of billions of dollars. It's like, you have to think like, is it another fusion energy thing where it's just going to be a money sink and it's not going anywhere? And it's all the people who are working on it are kind of wasting their time, so that could be possible too. So anyway, and it's also putting thinking people kind of to the side. That's also a thing, like people that think about things and try to understand what's going on are being pushed aside towards this kind of bureaucratic wasteland of just measurements, like getting numbers, so many numbers, and like more numbers are better. It's like the companies just patent. So like, yeah, there's a lot of like Chinese and Japanese patents, more than in the US. Most of them are worthless. And the reason, like people just are paid for patents, like to make a patent, it doesn't matter if it's anything of any value. It's like, then that just generates more and more patents, so it doesn't advance anything. Like nothing's really coming out better, Anyway, so anyway, that's kind of what's going on here. So anyway, yeah, the slices here that he goes through. So it's like so the first one is let me go through these. So the blue one is like the pure boron, lithium, but no barium. And he finds out there's a minimum for this lithium borate. And then the green one is no lithium, and he finds out there's a barium borate that's got a minimum energy or a maximum reaction. So it's going to drive to that product. And then they find out that, oh, the target one is right in the middle of this. So saying like, well, what if I mix that and that on the sides of this? And they find out, well, there was not enough driving force for that reaction to happen. So they're trying to find a pathway that would, if I put these two oxides together, then I would get the perfect, like it would get this huge driving force. So it turns out like these are the two oxides that you want to react to get to the product that they want. It goes directly there, and there's no side products to it. If you start with that lithium borate, barium oxide, then you can get directly to the product. So starting with these three isn't the right three to start with. You should start with those two. You get the product, or start with two that would generate lithium borate, probably lithium and boron, and then mix it secondly with the barium oxide, and then get to the product, like drive it down. Right, so that's kind of the theme. Like they're predicting with the DFT, and they're going to say like measure with the So he says like mix three, don't mix three, start with the LiBO2 first, then follow the purple pathway to get to your product is 192 milli electron volt. So out of the 220, it's like 80 or 90% is in this final pathway that drives it directly to the product quickly. So he ends up being that he uses 35 oxide precursors for this one of the studies. And he's going to get 224 measurements to show that this is the right answer. And they basically do that. And they find out that the answer is that. So then after that, he has his, I already went through the 5 rules, right? So then he comes up with the 5 rules, says that, and then he says the twist of the 5 rules, like with the other study, which is this. The other one is this the phosphate and lithium phosphate. It's trying to get to the lithium zinc phosphate product. Let's see. This must be a typo. Like it should be zinc oxide at one of the corners here. Like he's making a zinc lithium zinc phosphate. So he calls these ternary oxides because it's got the main metal, lithium, and it's got a doping metal, zinc. And he's got oxygen, and he's got kind of a non-metal dopant, this phosphate. So that's what he calls a ternary oxide. And that's what's called ternary oxide. The other one, I don't think this is really a ternary oxide, this other one, even though it kind of calls it a ternary oxide. Like these are all metals. Well, I guess boron's not a metal. Okay, so it is. So it's got lithium as a metal, barium's the dopant, and then boron is another dopant that swaps out the oxygen. There'll be lithium oxide and ends up being lithium barium boron borate. And so anyway, so that's what he means. He says in the beginning, like ternary oxides. That's that business. And then for this one, this should be, I think, zinc oxide at this corner. But anyway, he's gonna take slices out of this also and find out different pathways, so you could start from any oxide along any of these axes. So he's taking like the blue one, the orange one, and the purple one as possible pathways. And he's using this as a demo to say this one has a huge driving force to the product, so to get to this lithium zinc phosphate, but along that pathway there's a lower one. So in that case, if you mix those two together, you would get this lower one. It would skip right over the target one because you have a lower. This is an impurity. The impurity has a larger driving force than the thing you're trying to make. And here the driving force is too small, so basically the reaction wouldn't happen. And this one's just right. It's like the Goldilocks thing. So the just right one is the purple. Right, so you can see how the ternary diagrams are being used. Like you're going through some phase space and you're doing slices through it to see like, so you can see globally what's going on. And you can also do locally, like within one composition, kind of what things are happening. So that's kind of why I use a ternary diagram, which is, that's more or less what has to do with the chapter here. But anyway, so yeah, then he uses somewhere here he says, so this is his astral robot lab that he's somehow, I think he's borrowing it, kind of. So let's see, what does he say? The 3 trays of 24 samples can pass sequentially through astral every 72 hours. Powder dispensing is the bottleneck. And 24 sample trays prepared serially, whereas the firing and characterization steps can be run in parallel. So that's kind of hints on how to use the astral thing. So he's using that, he's in DFT. So he's got a software to calculate these energies, DFT calculate convex hulls. And he's also using literature information. And then he's using this materials project, you should probably glance at. It's kind of like to get information about materials. So he's feeding that all into his predictions to make the diagrams. And then he goes to the astral. He ends up with 3,104 reactions that he runs there to parameterize, to optimize. And all he's doing is checking the to see if his predictions from the DFT are right. That's basically what he does. So again, like normally this thing would be feeding into a machine learning, artificial intelligence, and would say like what the next mixture is going to be. Right. So, right. So that's where we are with this thing. So any questions on it? Or I thought it was kind of interesting. I mean, anyway, everyone's doing this. There'll probably be some talks that come in where people talk about robotics. Last year we had like 3 talks, people talking about robotic testing like this and chemical engineering, not in materials, but anyway. So it is pretty popular. I mean, this is like, I think everyone's kind of doing this, a lot of people. So this just describes what's going on in the paper. And then, so how do you determine the composition and ternary phase there? This thing is just asking you to go back to phase diagram, whatever. Let's see. Phase diagrams. So it's just saying the last slide or something is the ternary. Here, right here. So this gives you the rules of ternary. Like it's asking you to just spit out that. Explain how you determine the composition of ternary phase. So there's like 3 ways to determine the composition. You can do this way with the normals. You can do it with this vertex kind of way. Or if you have a scale on it, so you can see like he doesn't have a scale, right? So it's like you're on your own here. So if you want to know what's the composition at the yellow dot, well, you need to kind of, you could go from the vertex through the dot over to the other side and get the lines, the length of the lines, line segments, and then you can do that method with the line segments, this thing. Or you could take normals from the side and go to the point and then use the normal method, use that thing. And then you can't use the axes method because you didn't label the axes. Or you could go in and you could label the axes and then figure it out from that if you wanted. But then there's no there's no guidance to tell you where to draw the lines for the axes, right? So that becomes like kind of, so you go to, anyway, it becomes hard to do. Like you put your lines in, and you draw the line like there or there, so you don't know where exactly to draw it unless you have this grid already set up. You can figure it out. It's just harder to do. Harder to do that, I think. But these are pretty straightforward and hard to make a mistake. And then what do the 3 axes represent? So that each axis is like a pure binary mixture without the other component in it. So it's a mixture. It's like A, B, C. It's just A, B on that axis, and it's AC on that axis, and BC on this axis. Then if you take a slice along those axes like he did the first one, then it's a slice through that composition space with none of the other component. And then within his context, if he thinks that only binary, so you have a ternary mixture and only binary things react, or binary would react first, and there's no room for the blue to come in. So basically, you have to look at that diagram and that diagram first to see which one would be the first one to react. So you kind of have those two plots and then figure out which one has the biggest energy, and that's a dominant reaction, according to the way he's doing it. I mean, so it's not, this is kind of a kinetic driving force, would be like exponential of that over KT would give you the rate, but there's another option, which is the thermodynamic driving force. So you plot the chemical potential. And he shows that, so he does that in the supplemental somewhere. So he has this somewhere, there's a chemical potential diagram. Same comparison between the convex hull, which is this reaction energy, and the phase marked in the same color, and the right is a chemical potential diagram. So this is not a ternary diagram. I don't exactly know how to read this thing. He's got the three chemical potentials, the three phases, three oxides he puts in. I didn't really read how he would work with that diagram. Like, that seems to be kind of confusing. I don't know why you can't put the chemical potential diagram in a ternary phase space, but this is how he does it anyway. So that's that business. Yeah.
Basically, they represent material composition, the three X's.
They represent what?
Materials composition.
No, yeah, they do represent materials composition. Yeah, but so pure barium oxide is that dot, right? And pure boron oxide is that dot, and pure lithium oxide is that dot, right? So if I go from boron oxide to lithium oxide, all right, so barium, that's pure barium oxide, that's zero barium oxide all the way along that line. So it means that you have a binary mixture along the axes. It's a ternary diagram, it's got three components, but you only have two components along the axes. So if you want three components, you have to venture off the axes into the middle. Within the middle, you get three components. And to determine the composition there, you'd either go to the axis and draw the line and take the length of the two lines to the point, or you could do normals from it to get it. Normal from the line gives you the composition.
So they represent binary mixture of the materials, not the composition.
It's the composition of a binary mixture.
Okay.
So composition is okay, but binary mixture is the important part. Yeah. It's all composition. It's a phase diagram of composition. Or it's like an energy diagram of the composition. So every point in there's a composition. All right. Yeah, if you haven't worked with them, it's not that simple, you know. So you have to kind of just get familiar. Like but I think it's expected, like they threw this in nature without explaining what a ternary diagram is. This is expected that you know what those are. Nature is supposed to be like anybody could pick up a nature paper and understand it if they have a basic science education. Put it that way. So everything in here is fair game. Like it's basically, this is like the base level of what everyone thinks everyone should know about all the different fields, you know. Basically this is the level playing part. So supposedly that's the audience that these are written for. So, and he didn't describe what a ternary diagram is, so you'd have to figure it out. And again, like you'll run into this at various places. It could be like economics or something. You could talk about like mixing of whatever products on a shelf somewhere, or I don't know. You could have three competitions. You make a ternary diagram to show whatever price it is, or where the low price is, or something. You know, it could be anything on this kind of, it's just a way to plot things, but it's common to be used in materials, though, to talk about when you get more than a binary mixture, which is all the time. Like you're always going to be looking at more than binary. And the kind of the most number that you can plot is 3, you know, unfortunately. So other than that, you'd have to make a bunch of ternary diagrams, or have, I guess, well, yeah, you'd have to make a bunch of ternary diagrams if you have more than 3. That's kind of the point, I guess, but All right, so that's that question. And then figure one shows DFT results for mixtures. Four slices through the ternary diagram are shown. Explain what each of these slices pertain to and why the plots C, E, and H were made. So the three slices are the three. Let's see. There's more than three slices. What was it again? Figure one. Explain what each of the slices pertains to. Four slices through the ternary. Blah, blah, blah. So these two are the pure. So if you mix the oxides, only two can react, right, at a time. So boron with barium, boron with lithium, lithium with barium, lithium with boron. Right. So only two can react. So and that's his thesis. That's what he's saying at the beginning. Like his hypothesis is that two things react. The pathway is going to be the two things that react the fastest, right? So if you have this ternary diagram that he made with DFT, the things that are important under that thought are the sides, right? The blue and green sides are the important parts. So that's what he does. He takes the binary thing, which is his first hypothesis, and he shows what the energy diagram would look like that relative to the product that he's trying to make. I think he can't get the product because the product is a ternary product. So he's saying like those things would react first. The possibility of the things that they would make would be like everything along that line. Like if you're only going to have a binary at the start, then you're limited in the product, so it would go into the ternary mixture in the end, right? So and then the question is like which of those products would be the best thing to start with to get to that point? And he says it's this lithium borate and then barium oxide. Barium oxide is already one of the corners. Lithium borate is like a halfway down. It's not the best one, but it's here, but it's pretty close in energy to the best one. So it's possible to get to the lithium borate. And he shows like if you start with lithium borate and then barium oxide, which you have in a bottle, then you're going to get the best energy thing. You're going to get directly to the thing immediately. So you have this little trip down to lithium borate, minus 0.2, so 200 milli EV per atom. And then all of a sudden, there's this huge drop of 194 to get to the product from it. Right, so that's a good pathway to take. So again, like these are the binaries. Like you start with the powders, they're going to react as binaries. And then you can pick anywhere along that to mix two to get to the final ternary thing that you want. One pathway would be this orange one, which is a bad pathway because there's not a big drop in energy. And the other pathway is this purple one where it's perfect because it has a huge drop in energy. So that's what the things are there. The figure one shows DFT results, what mixtures of explain what each of the slices pertains to, why the plots C, E, and H were C, E, and H. That's basically what I said. Like he's trying to map out the energy of how you get to that product, not by considering all three mixed together, but considering binary mixtures, then picking off that to get another binary mixture would give a nice pathway. Then what is the vertical axis in B, D, and G? So he doesn't label it, right? There's no label. Like you're left to guess what that vertical axis is. But it's basically this energy, reaction energy. Like the whole thing's about reaction energy. So that's reaction energy just doesn't label it with the energy. I'm not sure why he didn't label it. I guess he thought it was simpler to not label it. He shows it here. Like he's not going to read energy off this plot because like what's the energy of the one in the middle? You can't exactly find it out from this plot. This plot gives you a feeling for like there's a minimum there, but it doesn't give you like to read the energy off this is like almost impossible, I think. I'm not sure how you would do it because it's a 3D plot and printed in 2D, so you can't exactly figure out what the energy is. You need to have it in 3D and tilt it up and then find it on the scale with it rotated, to see what the minimum of that is. There might be a way to do it. I'm not sure what it is. I don't think there is because you only have in the 2D you only have two numbers. You need three numbers to find out what the minimum of that is. So I don't think you can do it. Then see. Where would these things be on the ternary plots? So these are just barium boron, just two barium boron. So this is going to be along the barium boron side of the 3D plot. And then so those will be wherever the barium boron, like the green one. So basically those are going to be along this curve, and you can pick out where they would be. Where they would be in the 3D plot would be like, actually the green one's pretty easy to get because that's a projection straight onto it. So you can just pick out where they are along the x-axis. The x-axis, like that horizontal line, is the same whether it's tilted or not. So you can basically pick out where the compositions of those are. I think he has one of them labeled, or maybe not. They're going to be like these, one of these green dots here. Why is lithium barium borate unlikely to form? Yeah.
I understand. Well, the Ba3BO3. We can see Ba3BO3 will be in the end of the orange graph. Yeah, here, in the end of the orange graph.
Yeah, right. So that came from the green graph. So the orange graph is crossing the green graph at Ba3BO3. That point right here is on the green graph. So the green graph has to have Ba3BO3 on it.
So we have to explain only the green graph.
Yeah, it's saying like, where is it on this plot? So it's going to be on the ternary plot, it's going to be one of these green dots, I think. So let's see. So it's Ba3, what is it? Ba3BO3. So it's 1-to-1 BABO, right? Oh wait, but this is B2. So you want to have 50% B and 50% BA. In order to get that, I think you have to go closer to the B2 part. Like, in other words, this is adding two B's. You only want to get one B. So you go kind of halfway to halfway, like 25%. That would give you B. Let's see. You'd have to figure out how to do this. It's somewhere along this line. So you have, let's see. Oh, I didn't bring my pen with me. Okay, so here, let me just. Let me write down what this is. So we have B2O3. And then it goes to BAO. And then we want to get what do we want to get? BA3, BA, where's the say it wants? We want BA, we want BA3BO3, right?
Ba3BO3.
Professor,
Yeah.
you've not switched to the directory.
I'm writing down the things before I do that, because I can't see it here when it doesn't show up there. This guy gonna work. So to get that, so you need 3 BAs and 1 BO, right? So it has to, see, and you have the line, right? So you want 1 BO, but then these things are gonna give 2 BOs. So B and BA3. So B and 3 BA has to equal B2O3 and BAO times like X and 1 minus X. So even just the B, so 1 has to equal 2X. Well, 1 has to equal 2X. 1B, and then 3BA, 3 has to equal 1 minus X.
So can't see.
Oh, sorry, this thing does that. Oops, wrong way. I still can't see what's messed up, all right. This has to do with the lights, I think. One of the light situations is better. Not really very good. I just follow it down. That's worse. This is important. Auto. Auto good. I did this one too. It's not because of the light on them. Say. This particular one doesn't work very well. Brightness doesn't do anything. It's already on the dimmest brightness. That doesn't work and this doesn't work. Oh. Anyway, I have some markers. Definitely put the boundary in somewhere. Here. Right, extracted the markers. So we have let's see, B205 and BA is the axis, right? And you have want to get BA3, BO3. So this thing is like 2B. You have 2B, like X times 2B has equal B. And then BA3 is you have BA times Y or something. Right? So basically, Y has to be 3 and X has to be 1/2. So you're going to get from the BAO, it's going to be 3 over 3.5. And from the other one, it's going to be 0.5 over 3.5. So that gives you, it's going to be like 0.92 or something. This thing's 1 over 7. So like the other part of that is 0.08. Like that. So there should be like close to the BA at 92. Should be like right here. 92 over or something. That's how you do it. Something like that. Let's see how they show it on the thing, I think. So let's see. So it'll be 92 to the BAO. So it should be like it's mostly BA3, BO3, BA3. So it has to be like over here. It's got to be like up here. It's got to be closer to the BA. Oh, you have 3 of those and 1 of those. So somewhere like here. Composition should be like kind of like over here. The way I see it.
So we have to calculate the position.
Yeah, you have to calculate the position. I might have done that wrong, but basically it's something like that. Do a stoichiometry and figure out where it is. It's something like that, but then yeah, so for both of those, this one's BA3, it's got 2 BOs, it's gonna be further over towards the BO axis. It's gonna be further in that way. If you have 92, it's gonna be like 70 something. The other one. Yeah, and then why is LIBA BO3 unlikely to form? So I mean it's I guess it doesn't say in what context, but I think it's just talking about the orange one. I mean, it's unlikely because it's a low energy differential. If you start from those compositions. So if you start from is this starting from these two, or let's see, Li3BO2. Li3BO2 is here. So starting from that composition and then BaBO3. That's right, BaBO3, oh, it's not the middle one, so I guess they don't show the oh, no, they don't show the BaBO3 on this. Right, that's not BaBO3. It should be here, so somewhere here, the BA3BO32, which is the other starting point, but so, I mean, I think it's asking, it isn't really worded right, but why is it unlikely to form? I mean, in the context of the orange one, there's no energy. There's no energy to drive it, and so it's kinetically not going to form. Thermodynamically, it should form, but there's no kinetics to drive it. And then, so isopleth is holding the, these slices are isopleths. So it's holding the composition of one of the components constant. Like all these slices are isopleths through the ternary phase diagram. And then barycentric means that if you find a composition in here, it's already got the stoichiometry worked out. So it's the plots on this are, because it's a ternary diagram. So if I find a point here that's 50%, so if I find a point in here that the compositions have to add up, like if it's 20% B2O3 and 20% LiO2, it has to be 60% BaO. Like a ternary diagram naturally is baryocentric because it's got the compositions. Like the stoichiometry is already worked out in the diagram. If you have one point, you know the two components, you know the third one, they sum to one. Like a binary, the two would sum to one. Here the three sum to one, the compositions. So that's what they mean by baryocentric. So the logic behind this thing and why you would agree or disagree with it. So the logic's kind of that he makes some assumptions, you know. So you have to agree that the binary, like this binary concept has to make sense to you. In other words, the idea that if you mix powders together, then only two of the powders can touch each other. So only two can react. So it has to be binary reactions. That's the basis of this whole thing. So if you think that that isn't true, then this whole thing falls apart completely, because then you have ternary reactions and this whole scheme doesn't work. Right? So, I mean, you can say that doesn't make that much sense to me. Then this whole thing, that'll destroy this whole thing. Right? So it's based on that binary idea. Then should initiate between only two precursors, right? So basically, he's saying should, I guess. He's saying, I think effectively he's saying that it has to be that way. And then precursors should be relatively high energy. So basically you need a big drop in that plot to get the things to react. That kind of makes sense. Then the target, I mean, you know, basically you need a big energy drop for the things to react. Or the deepest point in the reaction. So if you have something like he shows an example in B where it isn't the lowest point in the reaction. He's trying to get the yellow and there's a lower point. Basically, you're not going to get your product in that. You're going to get this thing, zinc oxide and lithium phosphate, not the ternary or quaternary oxide. Composition is sliced between the two precursors should intersect as few other competing phases. And so these all kind of make sense. Like you don't want to have so you don't want to have like other minima along it, I guess is part of it. Like you don't want to have this situation, and you just want to have a pathway that isn't complicated, like very simple, goes to the product. Right. So if you have competing phases, or even when it's weak, like then a neighboring phases, like the orange phase would have almost the same driving force as that. That means when you try to make the yellow, the orange is going to form at 50% of it. So you'd have a large impurity in it. It wouldn't work out, right? So, I mean, they all kind of make sense. The only thing that might not make sense is that binary is the only way things can happen. And then you should have if you do have byproduct phases in the pathway, then you should have a lower energy in the byproduct phases. Like you should, so those are kind of just logical, I think. Like, in other words, if you have the orange phase in between, then you should have a lower energy in the orange phase. And then you need to have a deep energy also. Right, so that I think they kind of make sense. I just want you to go through and make sure that you kind of agree with it. And then this is just philosophy, like what you think about robots. The videos, and then like, is it really going to lead to something? Like, is this the way to go? Like, do you think, this is your generation, you're taking on the robots. So basically, you either are going to be on the robot side or the non-robot side. The non-robot side is going to lose. But to tell you that in advance. So basically, who do you want to side with in this thing? I don't think it's exactly like there's plenty of people that don't like robots because of science fiction movies mostly. I mean, that robots rarely play a good role in a science fiction movie, right? Like HAL or whatever from 2001 Space Odyssey was not a good guy. So, I mean, they might be good. I guess there's no reason to think that they're naturally evil, except that people made them, but basically it's there is this, is this just going to put people out of work? Like, is that the idea? Or is it, I guess I want you to say, like, from the perspective, it would be nice to have you say from the perspective of like different people, like your perspective, from the perspective, say, of science as a whole, like progress of knowledge, from the perspective of the companies, like businesses are pushing this really, because they see it like, right, the executive at Procter & Gamble doesn't have any idea what anyone's doing or what any of his products are, like no clue at all. All he knows is like the bottom line and the money coming in and money going out. He sees like the research group is just taking money and not producing any product. So obviously research isn't a good thing. If you can fire all the researchers and just hire a bunch of robots, that's pretty optimal, So from a brainless administrator point of view, this is great. Like, it's really replace all the grad students with robots. Then you don't have all the trouble of like visas or whatever. It's like, so this is a kind of, so you have to consider like different people's opinions about this. Like, robots is a political situation, actually. Like, when you get right down to it, isn't just robots. Like, they're replacing people, the car workers that used to make cars, now robots are making them. I mean, the UAW doesn't like robots, put it that way, or electric cars. So any kind of progress, they're kind of against. So that, so somehow maybe just think about it that way and say, like, you're reading this paper, it's like, think about the broader context of it. Because then nature, that means it's being pushed as like the future. This is like the way things are going to go. And like, you have a right to have an opinion about that. So you should express it if you can. Like, that's what E is. So you can spend a lot of time on E if you want, or you could just say whatever you want. It doesn't matter. And so I think it's important to think about these things and not just as like, yeah, it's a nifty science trick, like you can get a robot to mix this stuff. But when it comes down to like, is it actually going to make some progress? That's the issue. And then also, is it hurting people? Like, are people going to get displaced because of this thing or something? So anyway, that's it for this week. So successfully wasted this class period, but hopefully you get like more than just the thermal phase diagram thing out of this. So you can get a clue for kind of what people are doing. Anyway, that's it. I already went over. So any other questions or anything? So email me if you have problems with it, but if you can't figure out this thing, I might not have done this right, but basically it's some kind of stoichiometry calculation and figure out where the point would be on the chart. I probably did it wrong, but so don't do exactly that. Maybe that's right, but I have a feeling it's probably not right. Anyway, that's about it. Let me kill this guy.